Today is going to be almost entirely a review day because we did a lot last time with multivariate regression and standardization. So we're just going to go over multivariate regression and standardization again and do like a realistic example with a real data set of how you would actually approach a real problem using standardization. After we do that example, we'll talk about something called bootstrap, which is a way to get standard errors to quantify your uncertainty about effect estimates when you use standardization. And I'll give some kind of general tips about, how do you choose what confounders to adjust for, and how do you do study design that might help with your research notes when you get to that and use these methods. Regression is just a way to estimate what do you expect an outcome to be given that you observe certain values of predictors. And simple linear regression applies to the scenario where you just observe one predictor and you assume that the expected value of the outcome given the value of the predictor you observe is along some line. And you observe a bunch of XY pairs and you try to find the line, which is defined by beta 0 and beta 1, that best fits the data. And multivariate regression is really the exact same thing conceptually. The only difference being that you have more predictors whose values you observe that you use to try to guess the expected value of the outcome, given that you've observed those values of the predictors. And it doesn't actually look like a straight line because it's multidimensional, but it still has the same basic form where you assume that if you observe predictor values x1, x2 up to xp, then the expected value of y is going to be what's called a linear combination of those. It's just beta 0 plus beta 1 x1 all the way to beta p times xp. And again, you observe a bunch of data. So you observe a bunch of people's y and x1 through xp values, and you just try to find the best beta 0 through beta p values to fit the data, assuming that this model is true. So linear regression is a pretty simple concept in this sense. And this is really all we're going to need to understand about it for causal inference, right? It's just a way to estimate conditional expectations of outcomes given covariates or predictors under assumptions, right? Under the assumption that it has this linear. One thing you might want to do with a regression is predict an outcome, and it's straightforward how you would do that. The conditional expectation or the prediction from the model is just your prediction for the outcome. But another thing you might want to do is try to actually interpret the coefficients. And that gets messy when you're not in a causal setting, as illustrated by regression and other stories. They gave the example of predicting a kid's test score from an indicator of whether their mother completed high school and their mother's IQ score. And so this is the regression right here. It's the conditional expected value of the kid's score given the predictors is equal to beta 0, 26, plus beta 1, 6 times x1, the indicator of whether mom predicted high school, plus beta 2, 0.6 times x2, whether the mom's IQ. And the interpretation of each of the coefficients here is in terms of a comparison between groups who differ on the variable of interest, but have the same value of the other variable. So for example, the coefficient of maternal high school completion, which is 6 here. So if you compare children whose mothers have the same IQ, but who differed in whether they completed high school, then the model would predict an expected difference of 6 in their test scores. So it's a comparison between groups. And similarly, the coefficient for maternal IQ is comparing children whose mothers had the same high school completion value, but who differ by 1 point in IQ. The expected difference in the kid's IQ score is 0.6. Okay, so here's this long passage that we looked at before from Regression and Other Stories, which is basically saying that this type of interpretation is maybe not so useful and it's a little clunky, but it's what you can do with a regression if you're not in a causal scenario. So just in general, comparing two items like two kids, I and J, that differ by some amount on some predictor, but are identical in all the other predictors, the predicted difference in their outcome is the coefficient times their difference in the predictor on average. And as they say, this is an awkward way to put things, and it helps explain why people often prefer simpler formulations, which aren't really correct and can be misleading. And you just have to accept that regression, while a powerful data analytic tool, can be difficult to interpret. So that's when we're not being causal. Hopefully this motivates the desire to be causal, because usually causal questions actually do underlie most data analyses, and people settle for talking about associations because that's the best that can often be done because assumptions aren't met, but usually people want to be causal. So when are we allowed to interpret regressions causally? You need to be in a bit of a special situation where you have observed covariate, which we're calling L here, a treatment A, an outcome Y, and you want to know the effect of the treatment A on the outcome Y. So one way that you can satisfy this assumption called exchangeability is if you get to observe all the covariates that influence treatment and that are also associated with the outcome. So here, the only variable with an arrow into treatment and is associated with the outcome is L, and it can be associated with the outcome either by causing it or because some other variable causes the covariate and causes the outcome. It doesn't matter. This is a common way that in an epidemiologic study, you might hope to try to satisfy what's called the exchangeability assumption, because you can ask doctors, for example, what do you think about when you decide what treatment to give? And then you could get the full list of L's that are also associated with the outcome of interest. It's never going to be this neat, but this is an idealized version of what you might hope is satisfied in your study. There are other ways that you can also satisfy exchangeability. What exchangeability really requires is that if you fix all the levels, if you fix your covariate to any given value, like if you fix L, then there aren't additional variables that aren't in your regression that differ systematically with A and also are associated with Y. So that's what leads to confounding. That's what leads to like just the naive comparison of A equals 0 to A equal 1 subjects, not leading to a causal comparison. If just compare the Y's with people who have A equal 1 and people who have A equal 0 is a naive thing you might hope to do. The reason you can't is because the A equal 0s and the A equal 0 people and the A equal 1 people differ in ways other than treatment, which might be leading to their differences in the outcome, so that their differences in the outcome can't be attributed to treatment. So that comparison is not the causal effect of treatment. However, if you measure the right covariates, it may be the case that within the levels of those covariates, like once you fix them, if you compare people who have a certain value of L, any given value of L, just compare the A equal 1 people who have that value to the A equal 0 people, compare their outcomes, and association is causation. You actually get the conditional effect of A on Y in that subpopulation. So let's say exchangeability holds either because this causal graph up here describes the data generating process or for some other reason. But the key thing is that within levels of L, the A equal 1 and A equal 0 people don't differ systematically in ways that are associated with the outcome. Exchangeability holds, you can make causal comparisons. It means the difference of the expected value in Y, setting L to a certain value, and A equals 1, minus setting L to the same value, but A equals 0, is the causal effect of A in the group where the covariate takes that value little. Okay, so we have conditional expectations here, and we know regression models are models for conditional expectations. So enter regression. We can estimate these conditional expectations using multiple linear regression. And here L can have a lot of variables in it, right? And You can have interactions between A and L or between the L's, right? All those different types of multivariate regressions we talked about, you could use any of them to model this relationship. So if you fit a regression, then you're able to get this difference of the conditional expectations when A equals 1 and A equals 0 for any L using your fit regression model. And then the next step is if you want the average effect in the whole population, not just like conditional for a certain group of people who have certain L values, then you need to average these effects over all the L's. And the more people there are who have a certain L value, the more highly you should weight the effect in those types of people if you want the overall average in the population. And that's what standardization does. So the average causal effect in the population is the difference in the expected outcome had everyone taken treatment and the expected outcome had no one taken treatment. You can get that difference through standardization using this 3-step process. So step 1, fit the regression model for the expected value of the outcome given covariates and treatment. If there are no interactions between treatment and any of the covariates, then you're done after this step. You don't have to do the rest because then the coefficient of A in this regression is just going to be the average effect. But if there are interactions between treatment and any of the covariates, then you need to go on to these other steps as well. So step 2 is for each unit, subject, patient, for each person in your data set, you use the regression model that you fit in step 1 to get the expected outcome for someone who has their covariates. So once you fit your model, then you predict the expected outcome for each person in your data set, given their covariates and had they been treated. So with A equals 1. So whether or not they were treated, you set their treatment to 1 and you predict what their outcome would be with their covariates. And then you do the same thing with A equals 0. Whether or not they were treated, you set their treatment to 0 and you predict what their outcome would be given their covariates. And once you have all those predictions, then you estimate the average treatment effect as the difference of the averages of the predictions from step 2. So you just take the average over everyone in your data set of their prediction when A equals 1. And then you subtract that by the average of everyone in your data set of their prediction from the model at A equals 0. That's what I mean by E hat, the prediction from the model of the conditional expectation of the outcome given their covariates and had treatment equaled 0. The conditional difference is the effect only in people who have a certain value of the covariate. So let's say it's age, right? And let's say it's binary, like over 65 or under 65. The conditional effect, this difference, is the effect of treatment. Say you set it to 1. So then it's the effect of treatment in people who are over 65. And it's a 0 and get the effect of treatment in people who are under 65. And then the average in the population is some weighted average of those two effects in the over 65 and the under 65. And the weight that you assign to each effect should depend on how many people there are who are over 65 or under 65. So now that we've gone through it all again, let's do another example. And this one is a little bit more realistic. It's from a real data set. It's an example taken from chapter 13 of the book What If about causal inference. This is the chapter where they discuss standardization. So the data set that they use is called NHEFS, which is a longitudinal survey. They survey people on their habits and nutrition and stuff in 1971, and then they look at various outcomes in 1982 and also in 1992. And the question that we're going to use this data set to try to answer is, what is the effect of smoking cessation on weight gain? So the data set that we're going to use, it's going to be limited to 1,566 subjects who were smokers at baseline. So in their 1971 interview, they were smokers. They're considered treated if they quit smoking between baseline and the follow-up visit. Otherwise, they're considered not quitters. A equals 0 otherwise, so it's binary. The outcome is weight gain at the follow-up visit. And so this gets at someone's question about how do you know what interactions to include and what covariates to include. So this is the website for the book. Here's the data. I downloaded the data by just clicking CSV. So then that's how I got it into R. And here's the code book, which has a list of all the variables that are in the data set and the description of the variables. Scrolling through this, there are a lot, but it's not so overwhelming. There are 65. You can look at the ones that are baseline variables, so that were measured in 1971, to see which ones might be good confounders to look at. And what the authors of the book did, and what they acknowledge, is a half-hearted analysis that they invite you to improve upon. They make this table of covariates that seem to differ significantly between the treated and untreated groups at baseline. So age, sex, ethnicity, education, weight, smoking intensity, number of years that they had been smokers, whether they exercised, and I guess this seems related, but inactive life was another covariate. So these were variables that they thought were important to adjust for, either because they expected them to be strongly associated with the outcome or because they differed across treatment levels, or both. These were all thrown into the regression model along with the treatment variable QSMK, quit smoking. And the regression model that was chosen included what are called main effect terms for each of these variables. So just including the variables themselves, but then also square terms for all the continuous ones to allow like a flexible relationship. If you include a square term, it can be U-shaped. Let's say weight gain is being regressed against smoke intensity plus smoke intensity times smoke intensity, then that could be like a U-shaped curve instead of just a straight line. And then they included one interaction term, which was between the treatment variable and smoking intensity. So like the number of cigarettes per day. So they're saying they expected the effect of quitting smoking on weight gain might vary depending on how intense a smoker you were before you quit. So just to recap, we have 1,566 smokers. Some of them quit smoking between 1971 and 1982, some of them didn't. We want to know the effect of quitting smoking on weight gain, and we want to adjust for the covariates in this table, which we somehow chose as confounders to adjust for, things that differ systematically between treatment levels that might be associated with the outcome.